Chapter 5, Section 2. We're going to take what we learned in the last section about the quantum mechanical model and how that applies to the electrons and figure out exactly where are all the electrons and what configuration are they. So, an electron configuration shows us the arrangement of electrons in an atom. Atoms always occupy the lowest energy arrangement of their electrons, and we call this the ground state configuration. Summarizing what we learned yesterday, the first main energy level, or principal energy level, has one sublevel, and that one sublevel is an S sublevel. The second main energy level has two sublevels. It has an S and a P sublevel. You almost think of it as a concert stage and seats at a concert, where here is the stage and the seats closest to the stage will fill up first. So those are the lowest energy. And as we get farther and farther away from the stage, we get higher and higher energy amounts. So again, the first principal energy level has a 1s sublevel. The second main energy level has a 2s and a 2p sublevel. An s sublevel has one orbital. A p sublevel has three orbitals. That makes 4 orbitals total. The third main energy level has a 3s, a 3p, and a 3d sublevel. D sublevels having 5 orbitals. Fourth main energy level has a 4s, 4p, 4d, and 4f sublevel, and an f sublevel has 7 orbitals, which each orbital having 2 electrons. An s sublevel can hold 2 electrons. A p sublevel with 3 orbitals can hold 6 electrons. D orbitals can hold 10, and f orbitals can hold 14. So when you add up all the orbitals and together in each sublevel, that tells you how many can go in each main energy level. When I look at each main energy level, here's the 1s sub energy level with its 1s sublevel. It is of lower energy than anything in the second main energy level. So the 2s sublevel orbitals are lower energy than these 2p orbitals in the 2p sublevel. So the 2s or sublevel will have electrons before the 2p will. And the same thing with the 3s, the 3p, and the 3d. The s sublevel is lower energy than the p, and the p is lower energy than the d. So now we're going to talk about the 3 rules that tell us how and where each electron will go in the quantum mechanical model. The first rule is the Aufbau principle, and it says electrons go into the orbitals that have the lowest energy first. Any orbitals in the same sublevel have equal energy. So for example, all of the p orbitals in a p sublevel have equal amounts of energy. 1s is the lowest energy, but as you get up into higher main energy levels, some of the sublevels will overlap, and I'll explain that in just a second. When I start looking at total amounts of energy of each of the main the sublevels, as I get up here past 3p, I notice that the 4s sublevel here actually has lower energy than the 3d. So it kind of sneaks in there before the 3d. So as we put electrons into orbitals, we start down here at the 1s and adding more and more and more and more into the 3p, but then the 4s actually will get electrons before the 3d will. So each sublevel of orbitals gets electrons based on the number of amount of energy rather that each one has. Now, remembering how to which sublevel has less energy than another might be a little difficult, but I have a little way to remember. So you start out by writing out all of the main energy levels and their sublevels. So I have the 1s, and then right underneath it I'll write 2s and 2p. Then I write 3s, 3p, and 3d. Then keeping everything in a row. So 4s, 4p, 4d, and 4f, so on. And so forth. So then I began drawing diagonal arrows to show me which orbitals go first. So understanding that the 1s is going to have the lowest energy, it gets electrons first. After the 1s, then comes the 2s. The 2s sublevel gets electrons after the 1s. After the 2s gets electrons, then the 2p, and followed by the 3s sublevel. After 3s, then comes 3p, but after 3p comes 4s. Once the 4s sublevel gets electrons, then the 3d, 4p, and 5s sublevels get electrons in that order, and so on and so forth. And you can also have 7s down here, but that's as far as we'll go. The Pauli exclusion principle says that the quantum numbers of orbitals can only describe one electron. There are actually 4 quantum numbers, and they each describe a different thing. The first one is the main energy level. The second one is the sublevel. Then we have which particular orbital, as well as then within those orbitals the electrons spin. Some electrons spin clockwise and other electrons spin counterclockwise. Basically, the Pauli exclusion principle says no two electrons are exactly in the exactly same location. So when we're drawing and representing electrons to represent spin, we draw an arrow up to represent one spin and an arrow down to represent another spin. The third rule is Hund's rule, and I like to call this the sharing rule. Nobody wants to share unless they have to. So electrons are no different. So when electrons go into orbitals that have equal energy, we put one electron in each orbital until everybody has one, and then we add electrons after that. So for example, so here in picture A, I have one electron in this orbital, in the first 2 orbitals, and nothing in the third orbital. Then I add a third electron to the last orbital before I come and put a 4th electron in the opposite spin. Alright, now we're ready to put these 3 rules into place, into practice. And the first thing we'll practice is what's called orbital notation. We just draw a line to represent an empty orbital. We put the name of the orbital below the line, and you put electrons with an arrow up or down to represent the different electron spins. So here's an example of oxygen having 8 electrons, and this is what we would call the orbital notation for oxygen. So we're going to put this into practice. So for aluminum, I look at the periodic table, it has 13 electrons. So I start out and I write that the 1s orbital is the first main energy level, and it gets 2 electrons. Then the 2s sublevels have one orbital, and it gets 2 electrons. After the 2s, I look at the Aufbau principle, and I see that after the 2s comes the 2p. I know that p sublevels can have 3 orbitals. Each one can hold 1 electron. So I go 1, 2, 3, 4, 5, 6. So total number of electrons, 2, 4, 6, 8, 10. After the 2p comes the 3s. That's 12. And after the 3s comes the 3p. P sublevels having 3 orbitals and 1 electron there. So that accounts for the 13 electrons in aluminum. We'll do the zinc tomorrow in class. Now on to zinc. Zinc has 30 electrons total. And in that 30 electrons, we will again start with the 1s sublevel. So that's the lowest main energy level. the 1s sublevel, s orbitals having only one, holding 2 electrons. After the 1s, then comes the 2s, s sublevels only having one orbital. After the 2s comes the 2p sublevel. The 2p sublevel holds 3 orbitals, each orbital holding electrons, adding 1 to each sublevel, each orbital rather, at a time. After the 2p comes the 3s. The 3s can only hold 2 electrons. After the 3s comes the 3p. So again, 1 in each according to the sharing rule. After the 3p, according to the off-bell principle, comes 4s. So the 4s sublevel gets 2 electrons, and then after the 4s comes the 3d. D sublevels have 5 electrons. So I want to come back and count the total number of electrons: 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So there's 20 electrons up to the 4s point, and now I add more electrons. I need 10 more. So in the d sublevel with its 5 orbitals, I hit 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. So there's the orbital notation for 2 elements, aluminum and zinc. Okay, to summarize today, we talked about the off-bell principle, which is the order of energy of each sublevel in the orbitals. The Pauli exclusion principle, which says no 2 electrons are exactly the same and they get those opposite spins. And then we talk about Hund's rule, and that's the sharing rule where nobody wants to share orbitals unless they have to. The other thing we talked about was then putting these rules into place through the orbital notation and showing exactly where each of the electrons is in an atom.